Hello, everyone, and welcome to this explainer. Okay, so have you ever thought about what it would actually take to swap out the engine of a jet plane while it's still flying midair? Well, in the software engineering world, that is exactly what it feels like when you have to replace a foundational framework inside a massive monolithic codebase, all without halting production. Today, we are looking at a truly incredible feat of engineering from Uber. They pulled off what I like to call a massive scale engineering heist. They safely refactored their gigantic Java monorepo over to a new testing framework, and they did it without breaking the systems that power literally millions of rides and deliveries every single day. To really wrap our heads around the scale of this mission, we have to start with a pretty daunting number: 600,000. That is the exact number of legacy JUnit 4 tests that Uber had deeply embedded within their infrastructure. Upgrading, maybe a few dozen tests, that's a chore. Upgrading 600,000? That is an entirely different beast. It's what a lot of teams would look at and just flat out call an impossible target. And it gets crazier, because those tests weren't just floating around in a void. They spanned across 15 million lines of code. Think about that for a second. If you asked your engineering team to manually migrate 15 million lines of code, learn a completely new API, and transition all those custom test suites by hand, the drain on engineering hours would be absolutely devastating. It would completely stall any new product development. So, doing this manually? Totally off the table. They needed a completely different approach. Okay, let's dive into this. Here is the blueprint for our heist. We'll look at the 15 million line problem, building the infrastructure foundation, automating code with open rewrite, the master migration recipe, scaling the automated rollout, and finally, key outcomes and lessons. All right, phase 1, the 15 million line problem. Let's figure out why they had to make this massive move right now. The motivation becomes crystal clear when we compare the two frameworks. Look at JUnit 4. Now, JUnit 4 was functional, sure, but active development on it actually stopped back in 2021. That means no new bug fixes, no security patches, no new features. Staying on it meant they were basically stuck with dead tech. On the flip side, we have JUnit 5, which actually launched over 8 years ago. It offers enhanced, modern testing capabilities and, crucially, active support. But the sheer friction of migration had kept Uber locked into that old JUnit 4 system. However, with future JUnit versions planning to drop JUnit 4 entirely, making this shift wasn't just a nice-to-have anymore. It became absolutely critical. Moving on to phase 2, building the infrastructure foundation, specifically bridging the build. Because honestly, you can't pull off a successful heist without the right rigs. Before writing even a single line of JUnit 5 test code, Uber had a bridge to build. They had to unify their test execution under the JUnit platform. See, the JUnit platform acts as a sort of universal runner. It uses what's called the vintage engine for the legacy JUnit 4 tests and the Jupyter engine for the new JUnit 5 tests. But there was a major catch. Uber uses Bazel as their primary build system, and Bazel natively supported JUnit 4, not the unified JUnit platform. To fix this, Uber engineered a custom test runner. This acted as a vital integration layer. It handled all the Uber-specific test discovery, execution listeners, and flaky test filters, and then it delegated the actual execution to the JUnit platform. This was a game changer because it meant teams could start using JUnit 5 immediately, running side by side with the old tests. Which brings us to phase 3, automating code with open rewrite. This is where we get into safe, large-scale code refactoring. Now, what's really interesting about this next part is a concept called the LST, or lossless semantic tree. Look, the scale of this migration meant they needed a utility that could deterministically transform code without violating type safety. Doing a basic find and replace across 15 million lines? Yeah, that's incredibly risky. So instead, they chose an open source framework called Open Rewrite. Open Rewrite parses the code into an LST. This in-memory structure retains absolutely everything: type information, formatting, metadata, the whole shebang. Because of this, it allows you to safely overwrite the original source code without ever losing its semantic meaning. This was the exact precision tool they needed to crack the vault without setting off any alarms. But there was a hurdle. Open Rewrite didn't actually support Bazel out of the box. So Uber had to build their own custom Bazel aspect to act as a bridge. It works like this. First, the aspect collects the target source files. Then, it generates the full compilation class path so the system understands all the custom types. It passes these right into Uber's integration layer, and finally, it generates a code patch file containing all the transformations. They essentially built their own backdoor to allow open rewrite to securely process their highly unique environment. Let's move on and see how this fits into their overall strategy. All right, phase 4, the master migration recipe. This is the unified mega script that did the heavy lifting. They put together a unified mega recipe called JUnit 4 to 5 migration. But the absolute genius of this plan is that first bullet point right there, the precondition checks. In a massive code base, some files are going to use highly complex custom setups that standard automated logic might just choke on. Instead of forcing it and breaking the whole build, these preconditions acted as file-level filters. They only attempted to migrate the specific files they knew for sure they could successfully pick the locks on. If a file had unsupported utilities, cleanly skipped. For the eligible files, the recipe just went to work, applying standard migrations, converting custom runners, swapping out legacy base classes, and automatically figuring out any newly needed dependencies. Now for phase 5, scaling the automated rollout. Let's talk about orchestrating this execution across thousands of targets without causing a massive pileup. Uber built this incredible end-to-end automated orchestration script. It runs the open rewrite tooling, applies the generated patches and dependencies, and then, this is absolutely crucial, it validates everything via continuous integration test runs. If the tests passed, awesome, the success is preserved. But if the tests fail, a migration instantly auto-reverts and just reports the failure. This guaranteed that the entire system stayed perfectly stable. They got away clean every time. The migration literally only moved forward when the code was mathematically proven to work. And to scale this beast up, they utilized an internal tool called Shepherd. Shepherd automatically generated diffs for successfully migrated targets and basically pushed them through these CI validation loops over and over, checking not just unit tests, but integration tests, linters, and code coverage. And they did this iteratively. They would run a batch, analyze any log failures, build new open rewrite recipes for any missing code patterns they spotted, and then run the whole thing again. This continuous iterative loop allowed them to drastically increase their code coverage with very, very minimal manual intervention. Finally, phase 6, key outcomes and lessons. It's time to look at the results and some pretty fascinating reflections from this massive operation. And this brilliantly illustrates a major reality check for the tech industry right now. Uber explicitly noted, and I quote, "We attempted to use generative AI to migrate multiple test class files at once, but this approach was unsuccessful." In an era that is completely dominated by AI hype, it turns out that massive, precise, type-safe refactoring still requires deterministic tooling. AI was definitely useful for debugging, sure, but for structurally shifting 15 million lines of custom code, deterministic rules beat generative AI outright, no question. So the crucial point here is just how undeniably successful this centralized automated approach really was. I mean, check out these staggering metrics. They cleanly migrated over 75,000 test classes to JUnit 5. They automatically modified 1.25 million lines of code. They generated over 5,000 automated diffs. And they did all of this in just 4 months. By treating infrastructure upgrades as a deterministic engineering problem rather than just a tedious manual chore, they saved countless hours and totally secured their codebase for the future. Which leaves us with something pretty important to chew on for our own projects. Every codebase has technical debt, right? But Uber showed us that scaling amount of legacy code doesn't require a pickaxe. It requires a smart automated factory. So, what legacy dependency is quietly dragging your codebase down right now? And how are you going to automate its removal? Thank you so much for joining me on this explainer, and keep building.